Hi, today we'll be doing our continuation of the Java data structures series on Java. So we'll be doing the queue implementation of a linked list, or a queue using a linked implementation. So we'll be first starting with the QueueADT class. So it's an interface, so I'm going to create an interface. I'm going to right click my out folder if you're using IntelliJ, and then click new file. I'm going to type QueueADT, QueueADT abstract data type .java. You can choose interface if you can. For some reason it didn't show up that time. So I'll start with just defining the interface. So public interface QueueADT of generic type T. We'll be using generic types again. Generic types are good. They should be used in a lot of different languages. Well, they are used. So we'll continue that. We'll put some Javadoc here. So we'll say QueueADT defines the interface to a queue collection. So we'll say public void and queue takes a parameter T element. So also we're going to be using this interface for 3 different classes. I believe we're going to do this linked implementation, then we're going to do the array implementation, and then we're going to do a circular array implementation. So here we'll write adds 1 element to the rear of the queue. So I'll also be doing a diagram. I'll link it to this. I'll try to link it. If not, I'll do a part 2 with just a diagram to show you how the queue works. Basically, I'll just draw a little bit out in a sec. I guess I can just do it up here. So you have, let's just pretend these are queue indexes. So the queue comes from the rear and it comes to here, then it goes to here. And so here's the front of the queue. We'll just go like this, front of the queue. Here's the rear of the queue. So front of the queue is at index 0, then 1, 2, 3. So rear's at the rear of the queue is at index 3. So the values come like this. Let's just say this is a value. And we'll just put a comment here so it doesn't think it's a code. So the value comes from the rear. So it goes into the rear, it goes to the, like this, to the front of the queue, and then the value gets put here. So now the value's at the front. So if we're enqueuing an element, that's how it goes. It goes from the rear and then pushes all the way to the front. And then we dequeue an element from the front. Usually you can also dequeue it from, in a double-sided queue, you can dequeue from the, oh yeah, we're going to be doing a double-sided queue as well, using links, I believe. So we'll see all that, but when we dequeue, it's going to dequeue an element from the front, and then that's how it works. So if we put val1, then the next val, so if there's only one element here, let's just say we just enqueued an element and it's come to the front like that, then the next, let's say we enqueueval2, then it's going to go like that, and then enqueueval3. Then they're going to be waiting like that, like in a waiting line, like as we said. So the first person who gets to the line is going to leave the line first to get served by the bank teller or something. Then that value has left the queue. Then now val2 moves here, and val3 moves here, so they shift one, pretty much. Like that. Just say that's null. So that's how it works, that's how a queue works, at least a single-sided queue. So that's good for now. The diagram's going to be like that, except we're going to be using links, so it's going to be a little bit more confusing if you're new to links. So onQueue adds an element to the rear of the queue. It takes a param. So add param element, the element to be added to the rear of the queue. Whoops, sorry, I should have put it down here. Public void enqueueADT element, because we're gonna enqueue an element onto the queue, or in the queue. Semicolon for an interface, and then we'll do the next method. So for DQ, we'll say removes and returns the element at the front of the queue. Then we'll say at return the element at the front of the queue. So it's going to remove and return the element at the front of the queue. So here we'll say public, and it's going to return type T, DQ. And the reason why it returns type T and not void is because it's going to return the type of elements that we're going to instantiate when we instantiate in the main method. And it's not a void because it's returning something. So it's going to return an object of type T, or an element of type T. If we were just not returning it, we could just do void, but we're going to return it as well. So now we'll do first. So this is like top or peak with the stacks. That's what it does. It just looks at the top element, or the first element in this case. The element at the front of the queue, so returns without removing the element at the front of the queue. Then at return the first element in the queue. Then here we'll say public T first. Same idea, it's going to return the element and not change anything. So we'll do the next one. isEmpty returns true if this queue contains no elements. Returns true if this queue contains no elements. At return true if this queue is empty. And here we'll do public boolean. So returns a boolean, true or false. isEmpty, so we know that one. It's usually pretty common for the collections. Data structure, so we'll do the next one, size. We also pretty much know that one, so it returns the number of elements in this queue. return the integer representation of the size of the queue, public int size. So returns the number of elements in this queue. Return the integer representation of the size of the queue, or this queue, doesn't matter. Public int size, so returns the number of elements. We've seen that one before. Also pretty common, so now we'll just do toString. Technically it's not really in the interface, but we'll just do it anyways. Returns a string representation of this queue. Excuse me. Return the string representation of the queue. Excuse me, of the queue. So at override. Whoops. Public string toString. That should be fine. Not sure why it's not giving us this here. It's usually supposed to light up in green, but I'm not sure why it didn't do that. Unless I spelled something wrong. Should be okay. We'll save that. Then we'll start implementing a queue with links. So since operations work on both ends of the queue, we'll use both front and rear references, or header tail. Okay, so we're going to create a class called, I might have to, I have this already on my other computer ready to go for you guys, so I'm not sure if I have the right file, but we'll just create another class here. So we'll create LinkedQueue, LinkedQueueADT. You can do ADT if you want. I'll just do LinkedQueue, doesn't matter. Maybe just do LinkedQueue because it'll be easier to follow along if you're typing in your IDE. So public class LinkedQueue, QUE, of generic type T. We're going to implement the interface QueueADT of generic type T. That's fine. Should be getting an error unless I spelled it wrong. QueueADT of generic type T. QUEUE. That's strange. Unless I spelled it wrong. QUE. Where is it? It's not even here. That's strange. Can't find it. Q. What the heck? That is super strange. Okay, new Java class. I think it glitched earlier, so I'll just fix it real quick. Okay, there we go. So I'll copy everything in here, paste it in there. Should be good. Now I'll close that one because I can't even see it. Now we have that one. Okay, there we go, it works now, and now we're just getting an error telling us that we didn't implement the methods. So we'll start doing it. So we have public class LinkedQueue, generic type T, we'll just write here, in Java doc, LinkedQueue represents all linked implementation of a queue. ADT. We'll just do queue. It's already an ADT. So that's fine. Then we'll do the instance data. So private. Actually, can I not put this up here? So I'll just cut that and put it here. Alright, I'll just take this as a comment. Actually, you can leave it as if you want. I'm just making it a little easier to read, so I'll just paste that there. I like leaving this right at the top, unless there's an import statement. So here we'll have a private variable int count. So it'll have a counter variable as an int. Then private linear node. Do we have linear node? Yeah, we've already written linear node. So we're going to be using it again. If you want to see how we created linear node, see the linked stack part 1, or it doesn't say part 1, it just says link stack ADT. That one should be uploaded already. Just see that, and we go through step by step what's happening, or if you want you can just pause the video and copy that out. So we'll go back to this class. Well, then we'll create two object reference variables of type linear node. We're going to be using the linear node class for a long time until we move to trees, which will have a tree node. That's a little different because it has a root and it has like a sub root and has like two sub root trees, and we'll get into that later. So private linear node of generic type T head and tail. So two object reference variables of type linear node, and that's it. So here we'll just do some Java doc. I don't even need Java doc. We can just say public LinkedQueue. We'll just put here as the comment. Creates an empty queue instead of doing Java doc. Whoops. Auto formatting going on. So this is a constructor, or one of the constructors. Creates an empty queue, has no parameters. We'll set count equal to 0 and head equals tail equals null. I don't really personally like that way. It's basically head points to tail points to null. It's just a special way to declare two object reference variables, or to instantiate them. What we really can do is just set head equal to tail. I'm sorry, head equals to null and tail equals to null. So I guess it's just another way to, just another example. But that's fine, we can just leave it like that for now. So we'll do the next one in queue. Actually, let me just see my other code one sec. Excuse me for a sec. Just open up my folder. Queue linked list. Is this it? Nope. This is encryption. We already did that one. Singly linked list. No. Modified array stack. Nope. LinkedQueue. LinkedQueue of generic type T. Here we go. So this should be it. We have our interface. We have our linear node. Okay, so it's actually not too bad. Just NQ and DQ are the only really difficult methods. We'll just compare because I have two different versions of it. Okay, so we'll start with NQ. So we'll write a little bit of JavaDoc here. So we'll say it's the specified element to the tail of this queue. Then we'll say at param element the element to be added to the tail of the queue. So here, public void NQ, and from our interface we know that it takes a T element. Then here we'll create a new linear node object of generic type T. We'll call it node. Set equal to new linear node of generic type T, and we'll pass in element as a parameter. So if is empty, I know we didn't write it yet, but we'll just do that. So if is empty, so if the queue is empty, then we'll set head to point to node. So head's up here. Linear node of generic type T head is an object reference variable, and at this time it's null. Both are null at that point. And now we're going to set head points to the node that we just created here. So we can also call head front and tail rear if that makes better sense. Because I think in the notes we say it's front and rear, but that's okay. Sometimes we reference rear and front, head and tail. Just remember, if we say head, it can also mean front, and if we say tail, it can also mean rear. It's the same thing. It should be the same thing in most cases, unless otherwise specified. So we just have if is empty, head points to node. There's actually no brackets. You can put them if you want. I usually like to put them because then in a lot of code you'll see that then they'll have like an else on the next line, or like a space and then an else. But for me, I try not to space them out too much, so you'll see a bunch of lines together. But then we'll have else tail.setNext to node. So if it isn't empty, we'll say tail points to the next node. Then after all that, see there's a space here, but I'd rather just go under the bracket if there was one. But that's okay. Then we'll say tail points to node, then count plus plus. Really easy, just a few lines of code. We technically could put some brackets here, but that's fine. Because personally I don't like these kind of spaces in between the codes. I'd rather have something like this. It makes it easier for me just to see. For others it might not, but for me it does. But that's okay. We'll just leave it like that. So if isEmpty, we'll might as well just do the isEmpty quickly here. Count plus plus, yeah, we did do count plus plus. So it's the same as the other one, so public boolean is empty. You can just do equals to 0, but I do less than just in case there's a glitch somewhere, so return count is less than or equal to 0. Should be fine if you're doing an assignment, because it is empty if it's -1 as well. So that's fine, or less than that. We'll just quickly do size. Just takes a sec, so public int size. Return count. ToString will come back. First is easy as well, so we'll do first. Kind of stick these together, so public t first. Return head node.getElement. So our getElement is from the linear node class. GetElement right here returns the element that the node's holding. So when we create a node, we give it an element, and then we're just using a getter to access it. The reason why I stick these all together is because when I'm looking at one part, I want to be able to see more code. That's why I don't space them out. Some people may like to space them out and stuff. I may space bigger methods out, but that's okay. So for now, that's fine. So we have first returns the head element, or the first element in the queue. Boolean at the front of the queue, I mean. Boolean is empty size. ToString will come back. We're going to do a traversal later. So here we'll go back to this one now. So when we enqueue an element to the queue, we're going to create a queue in main. We're going to create a queue object, a LinkedQueue object. We're going to call it LinkedQueue lowercase. We're going to set it equal to new LinkedQueue, and then we're going to give it no parameters, I think. Then we're going to call that LinkedQueue.enqueue, or on queue. We're going to pass in an element, let's just say 5, a number, or a string, whatever. Then we'll create a node. If the queue's empty, head points to the node, and tail is still okay. So head and tail will both be pointing to this node, because we're going to be here. We're just going to start over. If the queue is empty, which it is, the head node points to the node we just created, this one. This else will get skipped. That's why I like using brackets. And then so you don't have to check which line's below which one. And then so after this else will get skipped, then we'll come here in the processing. Then we'll say tail also points to node. So at this point, both elements are going to be pointing to the same node. So count's going to be increment from 0 to 1. Then if we enqueue another element 6, we'll create a node, a new node, like node at memory location 2. Let's just pretend. Then if it is empty, which it's not, because now we have an element in the queue. Then we'll skip down here. Tail points to the new node, and head still points to the first node. else tail.setNext to the node. Okay, so tail.set its next, so tail is pointing to the first node, so then tail set your next element to equal, set your tail element to equal to the new node, so the first one's going to be linked to the second one, and then it's going to say, hey, tail, now point to the last node. So tail swaps, so that's fine, then count plus plus, so that we'll go through that. It's pretty simple. We'll look at the memory locations just to make sure. And then we'll do the diagram to just make sure you got 100%, because it can be confusing. So now we'll just do the last method, or the second last method, dq. Okay, so where did it go? Okay, I have it here. So okay, so we'll create a we don't need to create a space. We'll just actually, okay, did it automatically. So we'll say removes the element at the head of this queue and returns a reference to it. Then at return's already been written for us, so we'll say at return element at the head of this queue. Then we'll say at throws EmptyCollectionException. So EmptyCollectionException is this exception from the other class. So see linked stack again, actually linked stack part 2, and it's just an exception class. So it just calls the constructor and then calls the super method to call the super's constructor, and just set that up like that. Again, you don't have to do that. You can just print out that it was empty and return null if you want. It's up to you. We'll just do it this way. So public t dq, whoops, throws EmptyCollectionException. Oh yeah, by the way, after this series we'll be doing, it can take me a while to upload all these videos, but after that we'll be doing mobile app development. So we're going to be doing Android using Java, so that's going to be fun. And then we're going to maybe do some Swift, and then for Apple stuff, if not, we'll be doing also some Linux and C, which should be some easy stuff. So yeah, we'll be doing that. Just a sneak peek. So if is empty, we'll do throw new empty collection exception. So if the queue is empty, we're going to throw new empty collection exception, and it takes a parameter for the kind it is, so we'll just say queue. And that's fine. Then here we'll say t result points to head.getElement. T result points to the head node .getElement, and then we'll say head points to head.getNext, and then we'll decrement count by 1. So now it's saying, okay, if there was one element, and now there's, so let's just say, okay, we'll just say, okay, there's 2 elements, and we deleted 1. Yeah, so now it's going to say if is empty. Well, is it empty? There's still one element left. No. So that will get skipped, and then we'll just return result. Okay, so but if there's one element, so we have one element in the queue and we delete it right here, then oh, by the way, we can change this to save memory by setting something to null, because technically just the queue, it's the element still sitting there, it's just beside the queue, it's not linked to it, so it's not really being deleted. So if you're like creating an app yourself and you wanted to save space, then you could just delete those by setting them to null, so it would free up space and make stuff faster, or just free up space in general. So we'll fix that in a sec. But we're saying, okay, if the queue is empty, throw the exception that it's empty. That's optional, so we'll just we can just comment it out for now, just to keep it simple. So let's just say we're starting here. Public TDQ, we're starting on this line. T result points to head.getElement, so if we have 5 and then 6 in the queue, so 5's at the head, 6 is at the rear, or at the tail, then we'll say head points to head.getNext, so head points to 6, count minus minus. Now the element is not joined with the other one. Actually, no, that's a lie. So head points to head.getNext, so head is not 5 anymore, it's now 6. Count minus minus. If is empty. So if it is empty, tail points to null. If not, tail stays the same. So all it's really doing is just taking head and pointing it to the next one. So we'll double check that in the processing, because I feel like we can change this. But we'll just we'll do that in a sec. Sometimes like it's like you can make them better. You may read a textbook and be like, okay, I can make this better. Like right now it just seems kind of weird because nothing's really getting set to null. So we can change that. So T result points to head.getElement, head points to head.getNext. Count minus minus, if is empty, tail points to null, return result. Okay, then we'll just do our toString. And then we're done. That was easy, right? Except we haven't really debugged it yet, but that's okay. So toString, public string, toString. So it's telling us this is overridden. So we'll just do @override. See there, it changed to green. So we'll create a string str variable set to empty quotes. And we'll say linear node temp points to head, the head element. So while temp is not equal to null, while temp is not equal to null, or while head is not equal to null, str points to str plus temp.getElement. Plus tab and set a new line. Then we'll say whoops, temp points to temp.getNext. Return str. Excuse me, so what's happening here is we're creating an empty string variable that we're going to use to concat stuff. We're going to get the information here, so we're going to say, we're going to create an object reference variable of type linear node, named temp, and we're going to point it to head. So head's going to be, at this point, let's just say there's 5, 6, and 11 in the queue. Then we're going to say, so if temp is pointing to head, then it's going to be pointing to 5, because head's pointing to 5, and now temp's pointing to head, and then head's pointing to 5. Then, so think of them like blocks, like in the diagram, like there's a block, like a node block with some fields, and it's pointing to, that's head, and that's pointing to 5, and then there's a temp node with fields, and that's pointing to head, and then head's pointing to 5. You see that? Just imagine that, and then while temp, which is pointing to head, does not equal to null, so while head is not equal to null, then str, the empty string variable, points to str, the string variable, which is an empty string right now, plus temp.getElement, so 5, plus a tab, and then temp is set to temp.getNext, so temp is set to 6, then comes back up here, while temp, which is pointing to 6, is not equal to null, str equals to str, which is 5, plus temp.getElement, which is 6, plus a tab, then comes down here, temp points to temp.getNext, so temp was 6, and then temp is now 11. So I think we can debug that somehow. We'll do that, so we'll just go into main, QueueADT, we use that, linear node, we use that, okay. So we'll just write public class main, public static void main, string array args, the command line. Then we'll say LinkedQueue, not linear, LinkedQueue of type integer, LinkedQueue. It already had some kind of IntelliSense. Yeah, it knew that I was going to do lowercase. Maybe that's pretty common. In a lot of code you're going to write when you're going to instantiate objects, you're just going to be using the lowercase version because it's going to help you remember stuff. Even with like app development and stuff. So LinkedQueue of type integer object, LinkedQueue equals to new LinkedQueue. So we're just doing an instantiation of type integer objects. It's empty, and then that's it. Because in LinkedQueue in the constructor there's no parameters, so it's empty. So then now we'll do we'll call the onQueue method. Excuse me, just having some water, so now we'll call LinkedQueue. Should probably get a straw for my videos. That way you won't notice when I'm drinking. Okay, so LinkedQueue dot, and I don't have time to like delete that stuff, so I apologize. I have too many videos to make. So LinkedQueue dot, we'll just call nQueue. Then we'll nQueue 5. So we'll just check. So LinkedQueue, remember nQueue from our interface, it takes an element, t element. Then up here we've passed an element, so that's fine. We'll do the same. We'll just, actually we don't need to copy that, we'll just write it out. So enqueue 6, then we'll enqueue 11. I use the same numbers every time. What happened there? Oh, whoops. Dot enqueue. Okay, so then now we'll set a breakpoint, and then we'll save it, and then we'll just test first. We'll run it just to make sure we don't have any mistakes. We probably will. Okay, we'll not. Guess not. So then now we'll hit the debug icon. It's on the top right corner if you're using IntelliJ, which I recommend to use if you're using Java. Cannot find customer queue. Why is it calling customer queue? Can we delete these watches? Okay, there we go. So we'll just hit the bug. So LinkedQueue, that line's being executed. This one here. So we'll step into it. So we're going to go to the constructor. So remember, every linked queue has this instance data, has a count variable, a linear node object reference variable of type D, head and tail. And then here we're going to set count equal to 0. There we go, count is equal to 0, and head and tail both equal. Head points to tail and tail points to null. Not sure why they did it that way. You can just set them both to null. It's fine. They're both null. There we go. Then LinkedQueue.onEnqueue5. Step in. So linear node of generic type T. Node points to new linear node. So we're going to instantiate an object here within, so it's like a local object named node, passing an element which is 5. Step in. Okay, whoops, we gotta set up the node here. So remember, every linear node also has a next field and an element field as well for instance data. So then it's gonna set it up. This.element equals to element. Next points to null. There we go, our node was created. So if isEmpty, head points to node. So it is empty at this point. So we'll step into that. If isEmpty returns true if count is less than or equal to 0. Is count less than or equal to 0? Is it less than 0? It's not. Is it equal to 0? It is, so it's true. Step into it or over it. We'll step into that. Then head, we're going to say the head node points to node, which is the node that we're referencing in the scope, which is this one, which is node at memory location 956. So head is going to point to memory location 956. There you go, head points to, what happened to it? This dot, head points to memory location 956, so we were right there. And then this else got skipped because it was empty. So what we have now is we have our head node pointing to the node we just created at memory location 956 right there. There's our head node. There's our node. It's holding the element 5 or the integer 5. Then we'll say tail, which is right now it's null. So we'll say tail points to the node as well. So tail points to the node at memory location 956. So head and tail are both the same. There we go, tail at 956. Its next is null and its element is 5, so its next reference is null because there's only one element in the queue. And remember, we're on queuing it from the rear to the front. So now the head node is also 5 and its next reference is null, so both head and tail are pointing to the same object at the same linear node object at memory location 956. We're going to increment count by 1, and that's it. We're done. Then we'll go to the next one in Q6. So then we'll create a new linear node object of type generic T named node. We'll instantiate it. There we go, our linear node was created at memory location 1003. We'll say if is empty, we'll step into it. Well, is our queue empty? Well, let's have a look. We have this, or click our this tab for a LinkedQueue, which is memory location at 950. We'll click on it, and then we'll see it has a head node, which at memory location 956. So currently, both next are null, so there's only one element in our queue, or one object. It just has the memory location 956 holding the element 5. So is it empty? It's not empty, so it returns false. So this line gets skipped. We're going to go to else. So else tail.setNext to node. So it's going to say tail, which is pointing to that element. Set your next reference to the node we just created. I think actually there's kind of two ways to do this. You could also use head. But we're going to say tail, which is pointing to that. Yeah, I think there's two ways to do this. You could also say head.setNext to node. Personally, I feel like head would be the better way because head is what it's like. Head is kind of where you want to start traversing. You don't want to start traversing even from the back. Usually you traverse from the head in this case, especially if you're saying take your tail, which is pointing to the last node, and set your next to the new node, only because they're pointing to the same spot. But that's okay, so it's just going to say tail.set the next reference to the node. Right here at 1003, which is holding 6. So right now tail's pointing to 5, same as head, that's what we're saying. So tail and head are both pointing to memory location at 956, which at that memory location is storing the element 5. Then we're saying tail, take your next reference and point it to the node. So both head and tail are really pointing to that node that we created last time, which is 5. So it's kind of going like, okay, there's a head block pointing to the node 1, or not node 1, the node at 956, and then saying, okay, well tail is also pointing to memory location at 956. So what it's really saying is 956, take your next and point it to the next one. That's all it's saying. But we could have just used head to do it. So anyways, we'll take tail and set its next reference to the new node 1003, which is holding 6. So we'll step into that. It takes its next reference or field, points it to node 1003, which is holding 6. So here we go. Now you can see that both heads next and tails next changed, and the reason is because both head and tail are pointing to the same place, so that's why I'm saying it would have made more sense to do it with head. So if you're writing your own, you can change it. It should work the same. Excuse me. So we'll say we'll just check here. Head points to 956, tail points to 956. Head's next reference points to 6, that's fine. And tail's next reference also points to 6, so that's why I'm saying it's a little silly. So at this point it's going to set tail to point to the new node 6, which is 1003. So I will look head and tail at 956, so this tail is going to change. It's going to say, okay tail, point to node 1003 now. So this one. So that's going to change. Ready? There you go. Now it's changed. 1003. They're not the same anymore. And this one's next is null. Count plus plus. So now counts 2. We'll do it again. So we'll on enqueue11. So we'll call our object, then call the enqueue method. We'll create a node. Linear node. If is empty, that's false. So else tail set your next. Okay, maybe I kind of see why they're doing that. Because you don't have to traverse, but I think when I did this, I did traverse. Let's just see. So tail set your next reference to node. So tail, okay, so our queue has 5 in it and has 6 in it. Head node, which is 5, and then next is 6. Okay, so then tail, it just has its 6. So tail's pointing to the last node, so 5 and 6. So it's saying tail, which is pointing to memory location 1003, which is holding 6. Take your next reference and point it to the node that we just created. Which is the 11, because we just created a node here. That's now memory location 1024, holding the element 11. If it's empty, it's not, so skip. Then it's saying, okay, tail, take your next reference and set it to point to the node we just created, 1024, which is element 11. So it's taking that current tail reference, which is pointing to 6, and it's going to say, hey, take 6, which is, so it says tail, take your next reference, which is currently null, and point it to 11. So that's going to happen. So here we go. So tail is now pointing to 6, and its next reference is pointing to 11, and its next reference is null. So it's saying, okay tail, well we've changed now because we have a new tail, so we're going to redirect you to point to 11 now. So we're going to set tail is going to change from 1003, which is 6, to point to memory location 1023, which is 11. There you go, tail changed to 1023, 1024, which is 11, if I said that wrong. And then that's how it works. Count plus plus. What we could have done is we could have we could have put a while loop here while head dot get next. But I guess maybe this way is more efficient. I guess just the first node, or setting the first few nodes can be a little confusing, but it does work. Unless this was a double queue and we were adding to the front of the queue, then, or if we're calling a linked list and adding to the front, then we could use head here. We could go like this. We could just call head, which would make it better. So that's what I was thinking of. But this way works okay. So that's fine. So we can stop, or we can just step into. We're done. We have our LinkedQueue here. Head, which is 956, memory location element 5. The next reference points to 6. The element 6 at memory location 1024. Actually, sorry. So we have our LinkedQueue, then we have our head element, which points to memory location 956, which is 5. The element 5, then we'll say, okay, its next reference, which is at memory location 1003, points to 6, the element 6. Then its memory location at 1024, which is its next reference, points to 11. So that's our linked list, that's how it works. Or sorry, that's our linked queue. That's how it works. And then tail, you can also traverse back. Can you traverse? Actually, no, we can't traverse backwards, but we could if we had a previous reference, so we could make it a doubly linked list. We'll be doing that later. Those are fun as well. So here we could have a next and a previous, but these nexts are different than the link stack because they're pointing in the correct direction, like they're pointing right. If you're thinking about it, how it's going to be printed, then they're going to be pointing right. So look, it's saying, okay, look, here's tail. It points to the tail element in the queue, which is the last element or the rear element. It points to memory location 1024, which is 11, and there's no next because there's no element after that one, which is going in the right direction, going right, not left, which is like the link stack that they were going left, which was technically previous. These next are going right. But if we go to the head, we'll say, okay, well, this element's here on the left, like this, 5, 6, 11. So if we're looking at the tail, there's no next because there's no element here. There's just a null here. So look, tail, it's next. Well, there's nothing here because that comma, if that was a next, it's just pointing to null. But if we go to head, which is over here, and we'll say, okay, we're here, then its next is pointing to 6. So this next is going right, and then this next from 6 is going right to 11. So the next are they're correct in this sense because it's working properly. So we'll stop that. Then we'll call LinkedQueueADT. I don't think there's any parameters for that. There's not. We could add this. Well, we've been going for an hour already. That's okay. So we'll just finish that. Just get a sip of water again. So just run that in the meantime. Hit the debugger. Okay, so actually that's fine. Just stop it. Apologize though. So just put a breakpoint, change your breakpoints from here to here, then re-debug it. So now we're at this one, so it's exactly the same where we left off, except we'll have some different memory locations. So we'll step in, then we'll say, okay, if our queue is empty, well, is our queue empty? It's not because there's elements inside. Go here, so returns true if count is less than or equal to 0. Well, also, yeah, we have our counter, so it tells us. You can set it up differently though. Like if it traverses to the first element, then you can say, you could set a boolean that it's not empty, something like that. You can change it. You can use booleans. You can even use a print statement if you really wanted to. But in this case, we have an int variable and it's a count. And 3 is not less than or equal to 0, so it returns false. Excuse me. So we'll say t result points to head.getElement. So we'll create a variable here of type t. It's type t because the elements in the queue are of type t. Then we'll set it to point to the head node, which is at memory location 983. They've changed now because we've run it again. So dot memory location at 983, which is holding the element 5. So t result points to 5. We can see here result. Where is it? Whoops. There we go. Result points to 5 right there. Then we'll say okay. We'll remove watches. You don't have to do that, just to clear it up. Well, then we'll say head points to head.getNext. So head points to the head element, which is 5, dot get next. So head points to the head element dot get next. Again, tails, there's no previous, so if this was a doubly linked list, we would have to change something else here. We'd probably have to set them to null, which is a better idea. We can actually change that in a sec, but we'd have to change something for tail, because tail, there's no, if there was a previous, which there's not, there's just a next. So we'll just say, so right now we're just saying head node points to the head node, which is 5, dot get next, which is 6 now. So head is going to point to memory location from 983, which is 5, to 997, which is 6. So we can see head has changed to 983. Or hasn't even changed yet. Okay, now it's changed, so head points to 997, as we said. So head is now 6.